This video introduces physical planning with joint-embedding predictive world model. A world model predicts the future state of the world, given a context of past observations and actions. However, it's not suitable for planning. Latent planning trains a world model from state action trajectories and subsequently uses it to perform planning for new unseen tasks in the learned latent space. Joint-embedding predictive world model is trained on videos to learn latent dynamics for latent planning, not just for image representations for understanding images. JEPA-WM training and planning procedures are summarized in the figure below as shown here. This is a training procedure and this is a planning procedure. In the training procedure, this path observations, this frozen encoder, this latent states. The predictor uses the latent states and action to predict the future states. And then the trained procedure uses the start state and the action sequence to predict the future state. And then we use the loss on the final prediction and the goal state to train the predictor. The observations are embedded into a latent space by using a frozen visual encoder E5 and a shallow proprioceptive encoder E theta. An action encoder A theta embeds the actions. A predictor P theta on top of the encoder E5 theta takes the state and action embeddings as input. E theta, A theta, and P theta are jointly trained. For W path observations, O T minus W to T, and actions AT minus W to AT, the training objective on B element of the batch is defined as here and explained in this figure. Where the mean squared error loss error is computed pairwise between visual predictions and the target. The encoder and the predictor are vision transformer. The action and the proprioceptive encoders are linear layers, and their outputs are concatenated to be vision encoder output along the embedding dimension. P theta is trained with the frame causal attention mask, thus is simultaneously trained to predict all context lengths from W0 to W minus 1. The W is a training hyperparameter. The causal predictor is trained to predict the outcome of several actions instead of one action only. Given an initial and goal observation pair, OT and OG, each action trajectory, AT to AT plus H minus 1 is evaluated with a planning objective LP. The loss error is applied pairwise on each modality, where error VS is a loss between the two visual embeddings, and error prob is a loss for proprioceptive embeddings. When latent planning with a model trained with proprioception and visual input given alpha larger than 0, the planning objective error alpha p is defined as here, where the function f is defined as unrolling of the predictor from ZT on the action, with the maximum context length of W. We have this unrolling process. Where the unrolling function f could be a function of all intermediate unrolling steps instead of just the last one. Given a modeling function f, this similarity criterion, initial and goal observation pair OT and OG, A cross-entropy method is applied to fit parameters of time-dependent multivariate Gaussian with diagonal covariance. Cross-entropy method is shown here. We first sample an independent trajectories from a normal distribution. And then we update the action distribution to calculate action mean and action covariance. Repeat this procedure until we get an action sequence with a minimum loss. A random sampled ground truth prefix T1, Z1 to ZT, and the K-order prediction ZT plus 1K at a time step T plus 1 are concatenated and then fed to the predictor for the next unruly step to generate ZT plus 2, K plus 1. The training goal of the predictor is to minimize the rollout error, as shown here. This rollout will calculate the loss on the final state. For example, Z1 and Z2 are randomly sampled. The predictor P theta is first trained to roll out the first order embeddings from Z2 to Z6, 1 from Z1 using teacher facing as shown here. Teacher forcing, namely, we use the ground truth as input for each update. And then recursively call the predictor P theta to predict the next one using the concatenation of context Z1, Z2, and the prediction Z31 as input. This procedure is repeated until the rollout termination at the horizon, as shown here. This order 1, this order 4, unrolling in this direction. First, we use teacher facing to generate Z2 to Z6 1. And then we use in order 2, we put this Z31 as an input, concatenated with Z1, Z2 to generate Z4, 2 step by step until we get a termination state. For more details, please check with these references. Thank you. Bye.